All right, guys, welcome to our first week for online learning. So for this first week, you probably already saw there's 3 worksheets I put on there. The first one deals with vocabulary. I put a lot of pictures. I took a lot of pictures and posted on the canvas from the textbook. So there's a lot of reading for you guys to do, but this vocabulary sheet's really easy. You guys will get that done pretty quick. The second worksheet deals with the vocabulary as well. And what you're doing is you're just matching the definition with the vocabulary. Okay, and the last one deals with gravitational potential energy. That's what we're getting into this week is energy. If you guys remember last, in school we were talking about work, and work equals force times distance. So you're doing work, you're transferring, work transfers energy basically. So work includes distance, so you have to be moving to be able to do work. So if I'm pushing against the wall and the wall's not moving, so distance equals 0, it doesn't matter what my force is, right? Because anything times 0 equals 0. Okay? So to be able to do work, you have to be moving something. Now we're going to be getting energy, and as you remember, hopefully you remember, work is in joules. That's its unit, is joules. Energy, we're talking about now. Every type of energy is in joules as well. And write that out if you guys would like me to. Alright, so let's get into energy. Get rid of work. I also posted some pictures from the textbook on work. Reread those pages on work, because they'll be a great reminder for you guys. These pages in the textbook will be really helpful for you. Make sure you reread them many times. And make sure you listen to my lecture many times. Alright, so energy. Energy is to be able to move. For anything to move, it requires energy. For me to be able to talk to you right now, I'm using energy, right? So to be able to pick up a chair, or to be able to, for a car to move, it uses energy, right? It uses the gas we put in it. It breaks down the gas and uses chemical energy to move the car. So the law of conservation. I'm sure most of you guys have learned of the law of conservation before. It states that energy is neither created nor destroyed. Energy is just transferred. So we're going to be talking a lot about transferring energy. The first type of energy we're talking about is kinetic energy. And this is the formula for kinetic energy. Make sure you get to know this pretty good. Kinetic energy involves motion. So that's energy. That's how much energy when you're moving. We have velocity here. That's our motion. And we're talking about mass as well. So there is a problem in the textbook that I'd like to go over. Page 116, it says a jogger with a mass of 60 kilograms is moving forward at a speed of 3 meters per second. What is the jogger's kinetic energy from this forward motion? Alright, so it says that the jogger's mass is 60 kilograms, so this is what I'd do if I were you. I'd write out each variable that we're given. 60, you can write kilograms right here if you like. Moving forward at a speed of 3 meters per second. 3 meters per second equals our velocity, right? Units for mass is in kilograms, units for velocity is in meters per second. So all we have to do is plug it in. There's 3 variables here. They'll just always give us 2 of the 3 or 3 of the 4, and then we just have to solve for 1. So putting it in here, half the mass, which is 60, times 3, which is the velocity squared. So half of 60, 1/2, times 60 would be 30. And 3 squared is saying 3 times 3, which equals 9. So 30 times 9 equals 270 joules. Make sure you have your unit for joules because it's energy, kinetic energy. So kinetic energy involves motion. Remember that. Now let's talk about potential energy. Potential energy is the potential, how much energy something potentially has. So it's not talking about something moving, it's talking about something at rest. So if we're thinking of a basketball, if I hold the basketball right here at my chest, compared to above my head, it's going to have more potential energy above my head. Because when I let go of the ball, gravity is going to take it to the ground. So when I let it go and it's in motion, that potential energy is transferred into kinetic energy. So the higher it is, the more it's going to fall, so the more kinetic energy it's going to gain while it's falling. I just wrote this up so you can see what PE is. PE is potential energy. There's a couple different types of potential energy. The first one being elastic potential energy. I don't know if you'll see it as EPE, but elastic potential energy includes elastic, like rubber bands or balls that are squished when you throw them against the ground, and then they expand back to their normal size and bounce back up. Okay, so if you're pulling a rubber band back and you don't pull it back very far and you let it go, it doesn't have very much potential energy. So when you let it go, it's kinetic energy. The potential doesn't transfer. Well, it does transfer, but the kinetic energy isn't very great when you let go of it. When you pull back a rubber band really far, it has a great elastic potential energy, and when you let it go, it's going to have a great kinetic energy. Okay, so the more potential energy, the more kinetic energy it can have when it starts moving. The next that we can talk about is chemical potential energy. Chemical potential energy, like I was saying earlier, is like when we eat food. When we eat food, our body breaks down and breaks the chemical bonds, and then we're able to use that food as energy for us to move. Same thing with gas in cars. The car breaks down the gas, and then the car is able to use that chemical potential energy, right? Next, let's see here. I'm not missing one. Okay, next we're going to talk about gravitational potential energy, and this is what one of your papers is on. So listen carefully. We're just going to put a G there for gravitational potential energy. And the formula for that is mass times gravity times height. Mass, like we're saying already, is in kilograms. Gravity is in meters per second squared. And height is in meters. Okay? Those are their units. So if we're given a problem like on our worksheet, it's going to give us 3 variables, and we have to just solve for the 4th. On your worksheet, like I did here, I'll show you. I highlighted, you don't need to highlight it, but I just wanted to show you. For each problem, I wrote down 9.8 meters per second squared for gravity. We're never going to have to solve for gravity because we always know what it is. The acceleration for gravity is 9.8 meters per second squared. So off here to the side, I'm going to write gravity is 9.8 meters per second squared. And then we're going to do a quick problem on page 119. 119 says a 4 kilogram ceiling fan, so mass equals 4 kilograms, is placed 2.5 meters above the floor. So height is 2.5. You got to make sure you have a reference point, okay? You can say 2.5 meters, but you don't know what that's above. So 2.5 meters above the floor. And what is its gravitational potential energy? So we just got to plug in all 3 of these, and then we can multiply them together, right? We don't have to do anything else. Okay, so for sake of time, I'm not going to do that. You're going to come out with 98 joules. You just have to multiply them all together, and that's your GPE, or your gravitational potential energy. Pretty easy. So when you're talking about gravitational potential energy, and you're saying, shoot, sorry, I lost my train of thought. That's all right. Keep going. So let's see here. Gravitational potential energy. Now we can tie the two together. We're going to tie kinetic energy and potential energy together with mechanical energy. I'll give you some different examples, but mechanical energy, when you have a near perfect system, okay, a system is when things are transferring energy from one to another. When you have a near perfect system, then you can use kinetic energy plus potential energy equals mechanical energy. So just a quick example, let's just say that we're on top of a 10-meter cliff and we have a potential energy of 100 joules. Okay, that's our potential energy. I'm just going to write it below. Our kinetic energy is going to be 0 because we're not moving. Potential energy is how much energy we potentially have if we were to move or jump off the cliff into the water. So we have 100 joules, 0 joules here for kinetic energy, and our mechanical energy is going to be 100, of course. Let's say we jump off the cliff. These two are inversely related, kinetic energy and potential energy. So while we're falling, potential energy is moving over to the kinetic energy side. So that means potential energy is going down, kinetic energy is going to be going up. So that means towards the bottom, or at the very bottom, we should have 100 joules of kinetic energy and 0 joules of potential energy. Sorry, I can't talk. All right, so that means at every point in time, mechanical energy is always the same. This is a near perfect system, like us jumping off a cliff into the water. So we should have 100 and 100. So even in the middle, we could have 50 joules of kinetic energy in the middle, which would mean we'd have 50 joules of potential energy in the middle, which means we'll have 100 joules of mechanical energy. Okay, so when we're transferring energy, you'll see that in another example, mechanical energy is always going to be the same. So let's look at another quick example here. Let's say we have a baseball bat and we're swinging it and we hit a baseball. Okay, that baseball, it's not very high off the ground when we hit it, right? Maybe a meter. And then we hit it and it's going to go up, and then gravity is going to bring it back down to the ground. Okay, think about kinetic energy and potential energy. Kinetic energy deals with speed. Potential energy deals with height. Kinetic energy, at this point, the kinetic energy will be at its highest because we hit the ball really hard. So right off the bat, it's going to be as fast as speed. Potential energy, inversely, will be low because it's not very high off the ground. Okay, if we follow the path of the ball, when we go to the top here, its kinetic energy will be at its lowest point because that's when it's at its slowest. When it's going slowest, inversely, the potential energy will be at its greatest because it has the greatest height at that time, right? It has a lot of potential energy to be able to convert back to kinetic energy. So falling back down, this will just be like over here at the beginning. Kinetic energy will be at its highest. Potential energy will be at its lowest. Okay? Hope that helps a little bit. Another quick example, I won't draw it on the board, but it's like on a roller coaster. When you're at the top of the roller coaster and you're about to go down the big steep hill, you're going slow, right? And then when you start going down, you go faster and faster. At that top point, your potential energy is at its greatest. When you're up high, like maybe 50 meters or so, 150 feet or something. Okay, and then you have a small kinetic energy, but then your potential energy starts moving over to the kinetic energy side, and your kinetic energy is at its greatest at the bottom. Okay, when you're going the fastest, when you hit the bottom. All right, I'm not very good at drawing a swing, but let's just say there's a swing here. Okay. All right, yeah. Okay, so let's say we're swinging. It's not very good. Anyways, when we are at our highest point up here, or over here, our potential energy will be at its greatest. Okay, potential energy is at its greatest, which means kinetic energy is at its lowest. But down here at the bottom is when we're going our fastest. That's when our kinetic energy will be at its greatest. All right, these all are examples from the book, so be reading your textbook. Okay, so last thing I want to talk about is power. Power equals energy divided by time. So however fast you're able to transfer energy into power is how fast you're going to be able to run, or how high you're going to be able to jump. Okay, if you're able to transfer your energy really quick into power, then you'd be able to jump over a house. Okay, but humans we're not capable of doing that, right? So that's just a quick overview of power. Power is in watts. We know that from earlier in the this semester. Energy is in joules. And your time is in seconds. Alright? Let's see. I think that's basically everything we need to cover. If you guys have questions, let me know. But please be reading your textbook. That is going to be your best friend at this time. My office hours are Monday through Thursday, 2 to 4. We can schedule one-on-one Zoom sessions if you guys have questions or need more explanation. But this first week seems pretty easy for you guys, so let me know if you have questions.